By combining Boyle's law and Charles's law, we can solve gas law problems using the combined gas law. This is where we're not going to keep pressure or temperature constant. What you see in front of you is the algebraic expression for solving problems using the combined gas law. And as always, when you have temperature in a gas law problem, it does need to be expressed in Kelvin. So you simply take your Celsius and add 273. So let's see if we can solve a combined gas law problem. Here what we're going to do is take a volume of 350 milliliters at an initial set of conditions at an initial temperature and pressure and change it to standard. So we want to change our initial temperature, which is 45 degrees, into standard, which is 273 Kelvin, and our initial pressure here, which is 910, into standard, which is 760 torr. So we're going to be changing two variables. We're going to see how temperature and pressure affect this initial volume of 350 milliliters. One way of solving this problem is using our algebraic expression that you see in front of you. P1 V1 over T1 must equal P2 V2 over T2. And this is a 6-variable equation. We have 5 of the 6, so we're going to be able to solve for the 6. So if you'll cross multiply here and solve for V2, you'll see that your final answer here, that your volume is increasing based on the temperature and the pressure change. It has now become 360 milliliters. Now we can solve this problem by the fractional method instead of the algebraic method you see in front of you. And this kind of breaks it down individually into Charles's and Boyle's law to end up obviously with the same answer of 360 milliliters. So let's try the fractional method. In this case, let's focus our attention on temperature first. We see that our temperature is starting out at 45 degrees Celsius, but obviously we need that in Kelvin, so that would be 318. And our temperature here is going from 318 down to 273. If you recall, there is a direct relationship between temperature and volume. That means as one variable goes up, the other variable is also going to go up. If one variable goes down, the other variable goes down. Here our temperature is going down. So you know what? Our volume needs to go down as well. So if we want our volume to go down, we're going to need to set up a temperature fraction that is less than 1. So if we multiply our initial volume of 350 by a temperature fraction that is less than 1, and as you see in front of you that would be 273 over 318, then our volume will go down. We've also got to consider the pressure. Here we see that the pressure is going from 910 torr down to 760. So our pressure is going down. What type of relationship is there between pressure and volume? Well, there is an inverse relationship. That means as one variable goes up, the other one's going to go down. So here we see that our pressure is decreasing, so this means that our volume has got to be increasing. That means that we need to set up a pressure fraction that is greater than 1 so that our volume can increase. So a pressure fraction that is greater than 1 is 910 divided by 760. Once again, an inverse relationship between pressure and volume. We notice our pressure is going down, so our volume's got to go up. So if you multiply our initial volume, the 350, by the temperature fraction and the appropriate pressure fraction, you're going to end up with the final volume based on these two changes, which is the 360 milliliters that you see in front of you. So you can solve this problem using the algebraic method or the fractional method you see in front of you.